You have two waves that are given by the function d1 and d2. I think d2 is just a reflection of d1. But it didn't specifically say that. So what they're asking for is that since these two waves are interfering, and you can see that one wave is traveling to the right, the other one is traveling to the left because of this change in sign, uh, we want to look at the standing wave that's produced by the combination of these two. So for part A, they ask for the function for the standing wave. That's pretty easy. All you need to do is look at D, and we'll call that standing wave, or SW. And that's just going to be D1 plus D2. That's going to equal to 0.02 meters sine of 2.0x minus 4.0t plus 0.20, sorry, 20, not 02, 20 meters sine of 2.0x plus 4.0t. We can go ahead and combine this and say this is all equal to 0.20 meters times the addition of sine of this plus sine of that. So it's going to be the sum of these two. Now there's a trigonometric identity which looks at sine of alpha plus bravo, or alpha plus beta, and it basically breaks it down into sine and cosine. I forgot what the actual identity is called, but you can look it up online. Wikipedia has a list of trigonometric identities. So sine of alpha plus beta is equal to sine something, cosine something, plus sine something, cosine something. So it so happens that if you have a minus sign between the two terms in the argument of the sine, you will have the sine of the first argument times the cosine of the second argument minus the cosine of the first argument times the sine of the second argument. Oops, and not closed yet. And now we're adding it to the second function, and that's going to be then plus. Now there's a plus sign here, so this is not going to be completely duplicated down here. It's going to be sine of the first argument, cosine of the second argument. Now instead of a minus, it's plus cosine of the second argument, or sorry, first argument, times the sine of the second argument. And now we have the closed parentheses. Now, as you can see, just from putting one right below the other, that these two are the same, these two are the same. And because of this minus and plus, we're going to go ahead and cancel that out. So this ends up being 0.20 meters multiplied by 2 sine of 2x cosine of 4t. And lastly, this should equal to then 0.40 meters sine of 2x cosine of 4t. And that's going to be the function of the standing wave from these two waves being interfering with each other. So the addition of the two waves interfering with each other. Second part is you want to know the maximum amplitude at x equals 0.45. Well, that's kind of easy. All you really need to do is plug in 0.45 to the x. And then since we're looking at the maximum amplitude, we're looking at the max versus time, right? Because x is stagnant at 0.45 meters. So the maximum amplitude is a time factor. Now, we already know from previous experiences that when we want to find a maximum, we take the cosine trigonometric function to equal to the maximum value, and that happens to be 1. So the max value, and we'll just call it D max, I guess, of 0.45 meters is going to equal to 0.40 meters sine of 2.0 times 0.45, and that's the argument for sine. Cosine is just equal to 1. This ends up being 0.3133 meters. And that's the maximum amplitude at that particular point on that standing wave. Now for part C, we'll look at where the other end is fixed. So in order to find that, we are looking at the lowest frequency, by the way, for which the standing wave can occur. So we're going to go ahead and look at the standing wave as something that looks like that. This is the lowest frequency, is when a half a wavelength appears at the two ends right here. That means that at the other end, where this displacement function is equal to 0, that's going to be the other end of the standing wave. That's where it's tied down. So we look at the lowest frequency of the standing wave, and we see that sine of 2.0x goes through only a half a pi rotation in that case. And I'll tell you what it goes. So it goes through half pi rotation. Okay. So looking at, again, this function right here, we know that through space at the lowest frequency right here, that you're going to have a displacement function go up as x increases, and then it's going to go back down as x increases, right? So that means that this sine function, the sine trigonometric function, is going to go from 0 to 1 back down to 0. And we want to know what x value will make it go back down to 0. Now we know that when x is equal to 0, it's at 0 to begin with. But now we want to know what x has to equal in order to make the sine function 0 again. Well, we know from the unit circle that if the argument is equal to pi, so let's look at the unit circle real quickly. We see that this is 0, and we see that this is pi. We know that the y-axis goes back down to 0 when the unit circle goes around half a circle to pi. So that means the argument has to equal to pi for this function to go back down to 0, which means this entire displacement function goes back down to 0 as well, hence where it's fixed again. So we are going to say 2x has to equal to pi. And then the solution to that is then equal to pi over 2. So that is where the next location of this standing wave will be, such that it's fixed. Okay, such that the displacement goes back down to 0 and it's fixed. Part D, the maximum amplitude and where it occurs. So when we see a maximum amplitude, we're first of all the following. We're going to say that the cosine trigonometric function with respect to time is equal to 1. So we're going to look at the time in which the maximum amplitude occurs. And we're going to look at sine trigonometric function, and we're going to set that equal to 1 because we're going to look at the space in which the maximum amplitude occurs. And it so happens that we only care about the space. We don't care about when, we care about the where it occurs. We're going to go ahead and say that 2.0x has to equal, and let's look at this unit circle, the only time that it's maximized is when the function, the y-axis right here, is at 1, and that's associated with a sine function. So that happens only at a pi over 2 angle. So that means 2x, the argument in sine, has to be pi over 2 for sine to become maximized at 1. Therefore, x is going to equal to pi over 4. You could probably guess that because you know the other end is stationed at pi over 2. So you could see that halfway, you could guess that halfway is going to be the maximum of the standing wave. So the answer is pi over 4 meters, is the location of the highest amplitude. Now, where does the highest amplitude come about? Well, if we make x such that sine is the highest and then t such that cosine is the highest, we're left with 0.40 meters. And that right there is what the displacement is going to be at the very highest point. So we say that the amplitude A is 0.40 meters.